Savia, can you hear me?
Yes, sir.
ভিসি স্যার পরে জয়েন করবে, বুঝছো তো? আমরা স্টার্ট করে দিই, বাই দিস টাইম স্যার হতে জয়েন করবে, তো সেক্ষেত্রে স্যারের স্পিচটা পরে থাকবে। ইয়াং, আর
Okay,
ইউ
sir.
দেয়ার?
Yes, I'm here.
So our guest speaker, sorry, chief guest, Professor Fazlilai sir will join later. So
Okay.
what we can do is start, and afterward, I can introduce him with you. Is it okay?
No problem. Okay.
Okay. So Savia, you can start.
Okay, sir. স্যার, যদি হোস্টটা একটু শিহাবকে দেওয়া যেত তাহলে বেটার হতো।
আচ্ছা, শিহাবকে দেওয়া হয়েছে বোধহয়, আমি আবার চেক করছি।
স্যার, হোস্টটা কো-হোস্ট দেওয়া হয়েছে।
আচ্ছা, ওকে হোস্টটা দিয়ে দিব, তাই তো? ওয়ান মোমেন্ট,
জি স্যার।
আই এম চেকিং। His name is lost, I can't see. Abdullah. Okay, now Shihab, I have given Shihab the host opportunity. Okay.
Okay,
He is
sir.
made host.
Then I will start the session. Assalamu alaikum, everyone. Hope you all are doing well. I extend my warm welcome and heartfelt gratitude to our respected faculty member, honorable special guest, and wonderful participant for gracing us with your presence. I'm Rafin Sabiha, currently serving as an event management and operation coordinator at IEEE Student Branch and secretary at IEEE SPS and IEEE ComSoc, Joint Student Branch Chapter OST. Welcome you all to the sessions. I would like to request our advisor, A.K.M. Baki sir, to say something about the session.
Thank you, Sabiha. I'm taking this opportunity to tell a few words. My thanks to Associate Professor Dr. Yang of the University of Technology, Sydney, for accepting my invitation as the keynote speaker of today's webinar. I would like to thank all the faculty members, students, and other participants of today's webinar. My special thanks to the members of IEEE Joint Signal Processing Society and Communication Society Student Chapter and IEEE Student Branch of Ahsanullah University for organizing this webinar. Let me tell a few words about today's keynote speaker, Dr. Yang. I have had the opportunity to observe the dedication of Dr. Yang towards microwave and wireless applications during the years 2010 and 2011, while I was associated with Monash University, Melbourne, as a research fellow. Dr. Yang was a PhD student of Monash University during that time. In recent past years, Dr. Yang has proven his dedications towards teaching research, and microwave-related IEEE societies through a large number of publications and IEEE-related activities. Dr. Young has a very strong research profile in biomedical and wireless-related applications. Without extending my speech further, I am handing over the platform to uh, Shabiha and Shihab. Shihab, the mic is over to you. You can continue.
Uh, Thank you so much, sir, for your excellent speech. And I'm very happy, and we are so happy for our speaker. Now, I would like to say that this webinar is jointly organized by the Department of Electrical and Electronic Engineering, OST, and IEEE OST student branch, IEEE SPS, and IEEE ComSoc joint student branch chapter. This webinar is an excellent opportunity to exploit advanced manufacturing methods to open up new options in antenna design, microcircuit design, and meta surface design. Now, without any further delay, I would like to introduce our keynote speaker of the session. It is our immense pleasure to introduce our honorable speaker, Dr. Yang Yang, an IEEE senior member, associate professor at the University of Technology, Sydney, has a diverse career spanning roles in industry and academia. He earned his PhD in electronic engineering from Monash University in 2013. Dr. Yang is the group leader at UTS Tech Lab, focusing on 3D millimeter wave and sub terahertz technologies for applicants in beyond 5G and biomedical field. With over 200 international publications in microwave, millimeter wave, and terahertz circuit, he has received accolades such as at the CST University Publication Award in 2018 and the 2021 Leakage Infrastructure Equipment and Facility Award. Dr. Yang hold editorial roles in IEEE Journal and chair key position in IEEE chapters, reflecting his significant contribution to academia and professional sector. I think it will be in very knowledgeable and learning session for all of us. Then I would like to request our speaker to take the floor and continue the session. Thank you so much, sir.
Thank you so much. Can you hear me?
Sir.
Oh, yeah. Thank you. Thank you very much, Dr. Sabiha, for introducing my background and information about the topic. And thank you for the invitation. And I really appreciate the invitation from Professor Baki. And we know each other more than 10 years ago when we were both with Monash University. And that was really a precious experience working together back in that time on the microwave and wireless research activities. So yes, thank you so much everyone for your attendance attendance to this webinar regarding the topics about advanced additive manufacturing technology, particularly for microwave circuit antenna and meta-surface designs. So I'm Yang. I'm from Sydney, UTS in Sydney in Australia. So yeah, let's have a look at this topic together. So today's talk actually covers pretty much 6 sections. So I'd like to give a little bit background information about the research we are doing and why we use. Then we explain why we use the 3D printed technology, 3D printing technology for making the RF electronics and the circuits, antenna, or meta surface designs. So we pretty much look at the motivation about why. And then we together look at the fabrication process, and we call that additive manufacturing electronics technology. It can print both conductive and dielectric materials at the same time. So very interesting technology, happy to share. Followed with some design examples that we've been working on in the recent years. And then we quickly look at potential applications by using this technology and the design examples, followed with a conclusion. Okay, let's have a look at the background. So I think
Dr. Young, can I interrupt you?
Yeah.
First thing that your slide is again, it looks smaller, and
okay.
Our honorable former Vice lecturer, Professor Dr. Mahmood Fazlillah sir has just joined. So, okay. Sir, would like to say something before his presentation?
I think, can you hear me? Is it audible?
Yes, sir, you are
yes,
audible.
yes.
Okay, thank you very much. I'm very much interested, to listen to his speech first. Somehow, as I joined just now, I was a bit late. Sorry for that, because I had an appointment which I didn't remember. So what happens now, you will be talking, Mr. Dr. Young is going to talk about a very important topics today. In fact, the 3D topics had been 3D printing, especially, had been very much popular for some days, for some years, and the manufacturing process that he is going to talk about is 3D printing and the application of technology to the development and also the production of very complicated products is very useful to all of us, and we'll be listening the application or this concept for some new technologies for new products, and it will very much interested. It's very interesting for all of us who are very much involved with this latest technology, and the knowledge of Mr. Yang will be very useful to all the people who have joined. And thank you very much for agreeing to talk on these topics. And I hope everybody will benefit and will also be working together in the future for a better outcome. Thank you very much.
Thank you very much, Professor Elahi, and really, I'm really glad to see you here, and thank you for your kind words and warm message through the emails and here. Surely, I'd like to share the research experience and the knowledge we developed during the recent years together with our colleagues in different student branches under the HPE umbrella. And also, I'm sure that there will be a lot of opportunities. And so if for any questions or any particular topics that the students or the colleagues are interested, please feel free to share, and we can always discuss. Thank you so much. So, So yes,
you can continue. You can continue.
Okay.
Continue with the presentations.
Thank you so much. Okay. So Professor Baki, how about the slides here? Is that better or is it smaller?
Yeah, it's okay. Young, it's okay. You can continue.
Okay, so it looks good now, right? Okay.
Yeah, it's good.
Okay, cool. Thank you. So okay, first of all, we want to look at the application background about the additive manufacturing technology for electronics designs, right? So everybody now using the various technologies, and from smartphones to tablets to PCs or even some other wearable or intelligent electronic devices. And people are talking about 5G now. So what could be the scenarios beyond 5G or even 6G nowadays people are talking about? So one important concept here is reconfigurable intelligent surfaces that many researchers have been working on this field. So I think that if you've been working on researches in wireless, more or less you've been heard about this concept regarding the wireless processing, signal processing, or hardware designs. For example, the meta surfaces or reflective or transmissive arrays. So here I just summarized a couple of bullet points showing that what this technology is and what are the challenges this technology is facing from the microwave engineer perspective. So reconfigurable intelligent surfaces, if you look at this figure here, actually is very clear. So the intelligent surface is supposed to be very smart, can electronically control the beam pointing to the end users. If you look at this diagram, that the users can be someone using tablet or smartphone or any maybe a laptop or anything that can be portable or wearable. So it's kind of an intelligent service to communicate to bridge the communication between the end user and the base station outside the building. So, but like many other emerging technologies, RIS is also facing a lot of challenges, even though it has very, very clear advantages showing here, like it should be able to shape the beams toward the end user to efficiently use the electromagnetic waves in the free space. It should be able to generate multiple beam for multiple users. Say for the room environment, people might have multiple wireless devices, so multi-beam RIS is very, very demanding. And again, it's supposed to be able to integrate both transmission and reflection functions so that the beam can be directed to multiple rooms. So instead of just single room. But again, there are a lot of challenges here. So at the moment, one key problem is the RIS has been only considered for the deployment on the walls. So the researchers regarding the end user side there haven't been that many research progress in terms of the hardware innovations. So this brings a lot of opportunities for us, and which could also be very challenging. So the challenging items I just summarized here, like the reconfigurability, intelligence, and the surface-like, which means the design has to be with low profile, which can be easily integrated with other electronic devices, for example, the transceivers. So if you're interested in this concept, here's one YouTube link prepared by Professor B. Johnson that shows about this concept a few years ago. So there's many other application scenarios. I just quickly show some general concept here, so give you a little bit more information about how it might look like. So this is one paper published recently on IEEE transaction on microwave theory and techniques. It's talking about the potential application of using orbital angular moment beams to communicate with multiple devices indoor. So why we use OAM, orbital angular moment? So one major reason is that it can support a big data communication, right? And so here are the opportunities I listed here. So for future, so for beyond 5G, definitely millimeter wave or sub-terahertz frequency is gonna be more utilized. So which talking about those frequencies, because of short wavelengths, they cannot be deployed for long distance communication. So short range big data wireless transmission will be the next hot research area. So like showing this picture here, so the big data communication transmission scenarios could be device to device, or could be between the intelligent surface and the end users. So again, it should also be able to support multiple beams, which means multiple streams can be possible in the gigabit per second transmission. So OAM, the orbital angular moment is a technology that should be possible to achieve this target. So again, people are also looking at the transmission and reflection integration kind of meta devices to achieve these kind of functions. So there are many challenges there. From physical layer, as an RF engineer or microwave or antenna engineers, we always think about how to realize those hardware designs so that the engineers at the wireless communication level should be able to build their, to verify their and beamforming technologies based on the hardware provided. Again, some other challenges like how to generate multiple beams or multiple bands designs are challenging. Fabrication of those kind of devices also another challenging part, because people need to think about the the microwave materials or processing technologies, for example, 3D printing, to help to achieve those functions. Other factors would be like intelligence, which is reconfigurability, is also important. That means we need to apply some digital algorithm to control the variety dials or maybe pin dials to achieve those kind of functions. Otherwise, people might think about using some phase tuning materials to achieve the beam steering functions. Again, those kind of designs are supposed to be able to integrate it into the packaging technology that co-functioning with the semiconductor chips. So back to around 9 years ago, so the angular moment, the orbital angular moment concept was first mentioned by this article regarding the point-to-point communication at millimeter wave beam frequency band. But that paper was talking about potential big data transmission between the buildings. So that's very interesting because it's talking about how to improve the system capacity and utilize the spectral efficiency, improve the spectral efficiency, and also talking about broadband communication and spatial multiplexing purpose. Because if you look at the OAN beams characteristics, they are really a good technology to generate to utilize multi modes, and it can be 1, 2, or 3, or 4, or even more modes to be used for those kind of channels to achieve the big data communication. So if you are interested, have a look up this paper. It's talking about this concept. If you are new to this OAN technique. Early last year, 2023, there was one paper talking about 6G communication, future 6G communications. It's talking about the meta devices because meta is a big concept been very popular in recent years. And because everybody now is looking at beyond 5G and 6G communication technologies. So meta device is one of those kind of direction that people are looking at. So in this paper, people are talking about how to tune the three-dimensional varifocal function that can make it integratable into the electronic devices to because it has very broad applications for wireless communications and sensing in 6G. Especially this design was designed at 300 gigahertz in the terahertz range. So it will be really interesting potential candidate for terahertz communication. So if you look at this is one of the good paper if you want to look at, and because it gives one of the direction for future, thinking about what is a meta device and how it can be used for 6G communication. There are some other interesting technologies regarding the meta devices. For example, using the vortex beam. Vortex beam actually is the OAN beam for multiplexing communication. So again, this paper published on advanced materials in 2016. So you might want to look at that. There are many other papers, but feel free to do some search literature review about it. So meta device can also be used for the holograph imaging purpose for security and anti-counter fighting applications, and which is interesting. So we had to look at those kind of potential future technologies in beyond 5G and even 6G. Now let's look at some engineering perspective challenges. So antenna in package or circuit in package have been out there for many years. And so the research group from IBM actually mentioned a few challenges and some potential opportunities back in 2015. And one of the interesting direction will be the antenna in package, or the packaging technology could be together used with millimeter wave devices. So that means because this is one of the direction that to integrate the packaged antennas or circuits with the semiconductor chip modules. So that means one future direction that is definitely the highly integrated systems, the miniaturized RF modules for wireless devices, as shown in this figure here, reconfigurable with reconfigurable beams, which means the beam is supposed to be very intelligent, controlled by the chips. Again, this gives people an opportunity to think about how to integrate multiple circuits and antennas into the packaged devices. So this actually is one of the paper that we published together with the research group from MIT and Tsinghua University, and also one people actually now is working with South China University of Technology. This is one good example to show that how the 3D printed emitter device can be used together with semiconductor chips for the sub-terahertz sensing applications. So you can see that this the left image is showing the on-wafer transceiver design together with our design, the 3D printed metal lens. Then we achieve this kind of a co-design packaged system to improve the radar sensing range and the radar performance. So again, this is one good example that we want to look at together. We have one video recorded by the collaborator from MIT. So we will show that video in the later slides. So motivation. We now understand what's the application background about this technology, the using the 3D printing, and what are the future potentials. Now let's have a look why we use 3D printing, not other technologies. So if any of our colleagues here have been using 3D printing, you might feel that 3D printing is really, really good tool, research tool or prototyping tool to verify the concept. Because the 3D printer is nowadays are getting cheaper and cheaper and easy to access. So from the desktop consumer level 3D printers to the high industry level, high precision fine printing 3D printers. So 3D printing gives you the opportunity to prototype your designs, and from your concept to verify. It gives you a lot of opportunity to quickly verify your ideas. And the entry cost is low, because if you can even go to a lot of service provider to prototype your designs, and otherwise you can buy some consumer level desktop 3D printers and just build a prototype in your garage, and so you don't even need to go out of your house to make the prototyping. And also it gives you very flexible design capabilities to make some special shapes or customized shapes to make your electronics devices really, really well designed to meet your expectations. And also it's really good to protect your IP if you are running a startup, and it can also help you. It's a risk-free confidentiality, we call that, to protect your ideas. Again, it's also very good for packaging in terms of electronics and system integration. So I just take one example here to show why we use 3D printing. So the right bottom picture here is actually the traditional antenna in package design that you can see that multiple PCB layers are stacked together to make the multi-layer antenna in package and designs. But if we use the advanced additive manufacturing electronics device technology, and we can actually make the multi-layer antenna in package in a single print, which means you don't need any post-processing. You don't need to stack PCBs. You just need to make your design as perfect as possible and load it into the machine and print it. That's it. It's like a all-in-one all-in-one job. And again, advanced additive manufacturing printers should be able to print even the interconnections inside the substrate to make these kind of to give you a lot of design flexibilities, which we will show a few design examples in the later slides. Okay, So we had a look of why we use 3D printing. Now let's have a look why we 3D print why we additively manufacture meta surfaces. This is just one example. You can even use it for other circuits like filters or couplers or power dividers or antenna arrays or whatever passive device you wish. You can also integrate the varactor diodes and also integrate your biasing circuit with a passive device to make it active. But here, let's first focus on the metasurface device. So metasurface coming a long way from the one-dimensional to the two-dimensional, all the way to the three-dimensional device. So if you look at the three-dimensional metamaterial, or you can imagine, well, it's just like stacking the multiple 2D metasurface together to make your 3D metamaterial structures. So you can look at this paper published on Nature Photonics in 2014. It talks about the 1D to 3D meta designs. So different to those traditional meta material or meta surface designs, what we propose here is low profile 3D meta surfaces. What do they mean? If you look at this picture here, shows that if you look at, we call that 3D meta surface because it has three-dimensional information. It's not just a 2D planar structures. Even though the profile is very low, it should be typically around 1 millimeter or 2 millimeter or less than 3 millimeter thickness in one single substrate. But if you look at the inside details of the substrate, there are a lot of phase delay lines or the microwave circuits integrated into the meta surface. Let's take one unit cell, for example. We call that meta atom because in meta surface design, unit cell called meta atom. And we apply the antenna and the microwave circuit concept to design every single unit cell here. So for the top and bottom layers, we apply the antenna elements for the top and bottom. For example, here shows the top patch we use it as a receiving antenna, and the bottom patch we use it as a transmitting antenna to receive the EM signal and propagate through the phase shifters built inside the single substrate to make the polarization control and the phase control to achieve the desired wavefront manipulation. And then the transmitting antenna will propagate the signal out to the free space, and so that the EM wave through this meta surface can be dynamically changed by shaping the beam. It can be, for example, the beam can be shaped from one beam into two beams, or even three or four. And it can also shape the beam by changing the polarizations from between linear and circular, or maintaining linear, or converting the polarization with certain degrees. And it can also be used to like generate the vortex beams, for example, the OAN beams, like we showed in the application background. So that means this kind of fabrication capability, 3D printing capability, give us a lot of design flexibilities which cannot be easily done by conventional fabrication technique. Now let's have a look. So by using the advanced additive manufacturing technologies, we've been publishing a few papers in recent years. So I only listed the published ones. So there are still some others under preparation in fabrication or writing papers stage. So I think it's better to focus on those published ones first. So if you look at here, the additively manufactured circuit electronic technology being used for making the meta surface designs, and there are quite a few meta surfaces. That's why I mentioned a lot about the meta surface applications for beyond 5G. So you can see that we are using this kind of a 3D printing technology made a lot of meta surfaces for different functionalities. For example, polarization maintaining, spin decoupled beams, and also the dual beam generation by using 3D printing. And for example, if you look at this figure here, shows that the linear polarized beam can be converted to dual beams with circular polarizations in different in left hand and right hand separately. And we also achieved transmissive performance and reflection performance as well. And this design is just accepted a few days ago. It's talking about the simultaneous transmitting and reflecting the EM waves, because this is very desired for 6G, because people are talking about the intelligent surfaces to be able to transmitting and reflecting the EM waves at the same time. So this is a new paper. It hasn't been it's not early access yet, because it just accepted a few days ago. I'm sure that it will come out in the next week or two. Other designs like those Fresnel lens antenna, which is a classic concept that we apply it's a classic Fresnel lens principles to make the dual band meta lens design. So design at 75 gigahertz and 120 gigahertz dual band. And again, we also apply this additive manufactured electronics technology for making the 3D printed bandpass filters from the microwave band to the X band, sub-6 to X band bandpass filters. And we also printed the couplers designs, that we verify that this is really good technology for making not only metal surfaces, but also microwave circuits. And there are some more designs based on what we achieved, but they should be able to come out in 2024 later this year. Another interesting design was about 3D printed 140 gigahertz flat lens designs, co-designed with R5C transceiver module. And if you look at this picture here, it can be a part of the transceiver package. And because the idea is really interesting, so we were able to publish this this work on the prestigious IEEE ISSCC and extended to the GSSC journal. Okay, we had a look of the research background and why we need additive manufactured electronic technology. Now let's have a look at this printing process. So if you've been working on 3D printers before, so you know that most of the printers are single materials, right? Or at least can only print dielectric materials or metallic materials. You rarely see that a single printer can print both materials at the same time, which is true. And yes and no. Yes, it is because it is indeed very rare to see from the market that those kind of commercial printers are available. But there are indeed some printers there, but maybe it's just haven't been able to very well promoted on the market that people can have access to it. We have another review paper coming out very soon talking about the conductive multi and dielectric multi-material 3D printing technology. It will be potentially published on the proceedings of the IEEE, is talking about this kind of emerging direction. So we hope to promote this kind of a multi-material 3D printing so that people know that, okay, this technology is there and how it should be sooner coming to everybody to use it. Okay, let's focus on this topic here, focus on these slides here. So the 3D printing system we use here is the Dragonfly LDN printing system available at UTS. So this printer has two groups of printing heads, and for each one it has 256 nozzles, and so one group of nozzles is focusing on the conductive silver nanoparticle printing. Another one is focusing on the dielectric material, is kind of acrylates ink to be printed simultaneously, which means the conductive and dielectric materials can be printed at the same time, which is really important and ideal for making the three-dimensional vertically integrated circuits into a single substrate. So this process uses UV light and the infrared radiation lamps to cure the inks separately. The UV light is for the acrylate, and the infrared light is for the silver nanoparticles. So if you look at the SME images shown here, the quality of the printing is quite good for microwave designs. And we apply this kind of a process for up to 140 gigahertz designs, as you've seen that on that 140 gigahertz length together co-designed with that radar sensor. So that means it's possible to design some sub-terahertz meta devices or some electronic devices. So if you look at the process here, I just simply simply summarize it here. So because both materials can be printed at the same time, so the two lamps should be operating together at the same time. So like many of other additive manufacturing technologies, so the material should be jetted from the printing heads at the same time, which means the material should be laid out here, layer by layer. So, which means you can make the patterns, the conductive, the metallic patterns, and together with a substrate. So, for example, if you print the first layer patterns here, then you can print the second layer patterns. So then you repeating the steps 1, 2, you make your these kind of complicated structures into a single substrate. It can be some blind vias or drills, and some microwave circuits can be integrated into the substrate. You don't need to make your surface flat. You can make non-planar structures on the top, but the bottom has to be planar because additive manufacturing needs support. You can't just hang it in the air. So that's why one side definitely want it to be flat, and the other side you can make special shapes as you wish. We just demonstrate this picture here shows that a printed top and bottom view of this emitter surface. This is the internal structure, so you can see how complicated it is, and which we will look at this design in later slides. So now let's have a look at the design rule, because as a RF designers or microwave or antenna engineers, before we do any designs, the first question we want to consider is the design rule, right? Because as soon as you know the design rule, you can make your designs because you have to follow the rule. Resolution is one of the important questions regarding 3D printer, because then based on the printing resolution, then you know what kind of frequency you can work on. And also another important information here is the line or space between the traces. And the line means trace, line width, which means trace width. And because this technology should be able to considered for packaging applications, so BGA pitch is also another information that you have to think about it, because eventually you might want to solder the chips on the printed circuit. And minimum wear is also another important information, because once you make the wears inside the substrate, you need to know the minimum dimension. Of course, you can make bigger ones, but the frequency might be low. Other things like the thickness of the dielectric layers and also the thickness of the conductor layers. Probably not that important for the conductor layers thickness, because regarding the wavelengths, this is fair enough, because we are not working on the nanoscale wavelengths or microscale wavelengths EM waves. So I think everybody is also very keen regarding dielectric constant and loss tangent, because those two parameters are very, very important for making RF designs. The loss tangent determines the efficiency of your delay, and the dielectric constant determines your operation frequencies of your delay. It can also determine the size of your RF devices. So I just borrowed these slides from our industry partner, Another Dimension. It's talking about gives you an image about what can be printed and what can be done if you fully integrate all the possible electronic components into this for this packaging application. So yeah, there are some parameters here. So it's really about packaging, and just need to follow the rule here to if you apply this technology for making the packaged electronics. So the printer itself looks like this. It's portable. As you can see, you have wheels, so that's why it's very convenient. Yeah, we've been still what we have here in our university is LDM systems, but the latest one is called Dragonfly 4. Yeah, we collaborate with our industry partner to making the designs using Dragonfly 4, and we in-house fabricate using LDM RUTS. Okay, so we had a basic introduction about the advanced additive manufacturing facility we've been using. So now let's have a look at the design examples. So the first design example I'd like to share with our colleagues here is this kind of a AME. We call that additive manufactured electronics. So it's called, it means AME. So it's still being circular polarized collimated and vortex beam generation. That's an application by using this metal surface. So this was done by Dr. Jianfeng Zhu, who is now with South China University of Technology. The design was done almost 3 years ago, and we fabricated and tested in 2021. So if you look at this fabricated prototype, this shows top and bottom view and has a very low profile. You can see from here the edge is very thin. But for every unit cell, you can see that it has the transmitting antenna here with the U slot to reduce the size. And the top antenna is being used as a receiving antenna because the EM wave is coming from top side and then received by the receiving antenna and propagated through this phase delay line. And that because this is the first design trying this concept, so we made a very simple structure. It's just one single phase delay line together with a pair of transmitting and receiving antennas to manipulate the EM waves. So this slide shows that once we propose a group of meta atoms, and then we need to work out the phase mask for the meta surface, and we rotate the transmitting patches on the to be distributed on the meta surface aperture to based on the generated phase mask to achieve the required beam shaping effect. So you can see that we combine the two phase shifts concept. One is a traditional transmission line phase shift generated by using the transmission line here. So you can make it longer or shorter for different unit cells to achieve the required phase shift along the TL line. Another phase shift is introduced by the rotating the transmitting patch antennas to achieve the PB phase shift. So the receiving antenna we keep safe and we don't rotate it because we only need to rotate one side, which is the transmission side. By combining both transmission line phase shift and the PB phase shift, we can generate the proposed 8 unit cells. We call that 3-bit meta atom, which is from bit 000 to 111. So if you look at the phase shift performance from 16 to 18 gigahertz, they are pretty linear, which is really good for making the meta surface design in that frequency band from 16 to 18. This figure here shows transmission at magnitude from 16 to 18. Because it's kind of optimized, because you can't make every single unit cell perfect, right? So we just try our best to balance that to make sure that most of the unit cell can meet at least 80% transmission coefficient. Yeah, of course, in the center frequency, you should give the best performance, but towards the end, the 16 or 18 gigahertz, the performance is getting worse, which means transmission efficiency is getting lower, and the whole efficiency of this middle surface is getting lower. This figure on the right hand side shows that how we achieve the right hand or left hand circular polarized beams by rotating the transmitting antenna. You can see that if we rotate the transmitting antenna by 60, for example, 60 degrees, the generated left hand and right hand circular polarized beams can have a separate phase shift towards two directions. One is positive 60 degrees, another is negative 60 degree, so that we can generate the two different circular polarizations. Again, this phase shift has to be combined with the transmission line phase shift, because this is just because of how they are connected here. The key formula we applied is showing here. So because if you want the deflected beam to be directed to a certain angle, then we have to define the angles. As a designer, you want to give a definition about angles you wish the beam is supposed to be pointing to. Then we just use by applying this formula and just define the theta, the theta and the phi separately, and x, y are coordinates along the middle surface, and f is the focal length. So f is optimized value, so based on your experience. So you can just start from the typical wavelength, or depending on your design, you apply it here and you optimize this value. But if you want your beam to be directed to 15 degrees toward one direction or 30 degrees, you can just substitute those values here to make your calculated phase element on the phase mask. This is a design procedure for this kind of a meta surface design. So step one is you define your beam deflection angles by using the equation above, and then you substitute those values into the equation to calculate the required phase distribution on the meta surface. So by rotating the angle, the transmission antenna's angle, for example, showing on the left hand here, it tells you that what's the expected phase distributed here. You have to combine the two to build to work out the phase mask required for your meta surface. And then the last step is just build a 3-bit unit cell or 3-bit meta atom from 000 to 111, and then apply those elements into the phase mask into the meta surface aperture based on the calculated phase mask. So of course you can use 4-bit, 2-bit, or even 16-bit unit cells. So it really depending on how you come up the groups of unit cells. The more unit cells you have, the more complicated your design approach will be. So eventually, a lot of people are using AI, artificial intelligence, to assist making those unit cell designs, which should be very brilliant. But a lot of challenges again regarding the AI algorithms to be applied here. So this shows one of the examples that we demonstrated in the paper. We defined the deflected beam with plus 15 and minus 15 degrees, and along x and the y direction. And you can see from here, the EM beam is clearly split into two collimated beams. if you can see here. One is left hand, another is right hand circular polarized. So those two figures shows the measured beam performance. Again, we calculate the required phase mask to generate OAN beam, which is also the vortex beams. And you can see from the simulation results here, two donut shape vortex beams are generated. And this is a wavefront by cutting from the X and Y. The second design example I'd like to share is the dual beam circular polarized collimated and vortex beam generation. But the function here is different, because if you look at this figure here, this design actually is talking about a function of converting the polarizations with certain angles between the input and output waves. Regardless of the what is the input polarization. Again, this is just can only manipulate linear polarizations. So if you look at this diagram here, so if, for example, if your input signal has a 0-degree polarization, then it can be converted to, for example, 10, 20, 30, or 45, or 90, or whatever degrees you wish. You can define those when you make the unit cell design. You can define those unit cells and to make sure you calculate the phase mask precisely to make sure they achieve this function. So the concept here we apply is called Poincare sphere. We work out the required phase distribution based on this concept. First of all, we need to propose a set of meta-atoms for circular with a circular birefringence characteristics, and then we rotate the angle determined by the retardance between the meta-atoms to eigenpolarizations, namely the right hand and left hand circle polarization. So we have to, at the same time, we have to make sure the Azuma's angle 2 pi is constant between the input and output, so that you can maintain this kind of you can achieve the polarization conversion regardless of your input polarization. So this one is kind of special and complicated. We need to use 2 pairs of differential feet, which is showing here. The red color means 1 pair of differential feet. Another blue color shows the second pair of differential feet connecting the receiving and transmitting antennas at the same time, so that they can make sure that no matter what polarization it is from the input signal, it can always be converted to certain degrees at the output side. So this is, again, we apply the 3-bit meta-atom unit cell designs from 000 to 111, and the phase delay lines applied between the transmitting and receiving antenna are complicated. So those are the parameters in millimeter defining the different lengths of the phase shifter. This shows that the between 26 to 32 gigahertz in the Ka band, we can see that it can maintain very good linear performance for those 8 unit cells. So that means they are good for making the meta-surface designs. The next, then we just follow the 3 steps mentioned above to calculate the required phase mask on the aperture. Then this slide shows the results in simulation about how those we apply with different input signal with different polarization, and we observe the output signal and see whether or not it can maintain the required phase polarization conversion. You can see that if the input is from 0 degree and you achieved the co-polarization achieved 45 degree minus 45, another is achieved 45, because this is dual beam. And if you input signal 30 degrees polarization, you can see that it can be shifted by minus and plus 45 degrees, similar for the 45 degrees input. So they maintain pretty well, and the magnitude can even be even better than the single end design. This is a differential end, and which always better to reduce the noise and improve the efficiency. It's almost 90% efficiency, which is pretty good. Again, if we make up the metasurface design with 90 degrees polarization conversion, you can see that it's also very good. You can achieve the 90 degrees polarization conversion. So this is a this is internal view of this design. You can see that some unit cells really complicated, and the phase shifters actually is very long, has a very long transmission line. So you just need to make sure that you fully utilize the space inside the substrate to make a long transmission line to achieve the required phase shift for that unit cell. So yeah, again, this is not easy to be done by traditional fabrication, so that's why we made it. We achieve it by using this AME technique. If you look at the prototype we fabricated from outside of the metal surface, you can't really tell anything, because the most challenging and interesting part actually was fabricated inside the substrate. You can't see from outside. They are underneath the top antennas, and you don't know how complicated they are inside here. This is a measurement set up in the antenna chamber. It's in the Ka band. So this is just shows the measurement and the comparison between the measurement and the simulated results. You see that we can generate the measurement phase frame and the wavefront and the magnitude in terms of magnitude and the phase are very similar to the simulated ones. You can even see clearly that this is a one mode, and this is -1 and another is +1 performance. We measured in the lab. The third design we want to introduce is another concept we proposed is kind of an antenna circuit antenna concept. So we call it circuit because this time on top of the phase design performance we applied by using the transmission line. We cross those transmission lines between the transmitting and the receiving antennas to convert the polarizations from X to Y or from Y to X, which means the main polarization will be suppressed, but your cross polarization will be enhanced in the output. So this kind of function, we take advantage of the crossover circuit to achieve this concept, which means if you look at this diagram here, if your input signal is with X polarization, then it will be converted, the X polarization will be strengthened, and so at the output side, you can only see a very strong cross polarization. Similarly, the Y can be converted to X, and the right hand can be converted to right hand, and the right hand can be converted to left hand. So this is very interesting design by applying this kind of antenna circuit antenna concept. Again, antenna is on the top and the bottom, so the circuit, microwave circuit, is built inside the substrate. So instead of just talking about the unit cell structures, and we just summarize some highlights here. So this is another class, a good example about antenna circuit antenna concept we applied for this metasurface design. We applied the PB phase concept to achieve the spin decoupled beam shaping, and we also combined both the phase delay line concept together with the PB phase shift to achieve the required phase shift on the phase mask, on the aperture, on the metasurface aperture. So we don't need to So those designs actually fabricated by 3D printing. So that means complicated antenna and the circuit structure can be made into a single substrate. We use this concept to generate the orbital angular moment beams with different topological charges. We show some example experimental videos, which is very interesting. And this is selected as an internal cover page by Advanced Optical Materials with Q1 journal, and it's good to see that the associate editor is very interested in this design, gives really good comments, which we just show some here. So next slides, I want to show the results we observed in our lab. You can see that this is a mode 1, OM mode 1, which is you can see the magnitude and the phase distribution. Those are the magnitude with a donut shape with a mode 1. Mode 2 has a bigger donut shape look like, and this is mode 3. You can see that this is even bigger donut shape. There will be like 3 circles of phase distribution. That means this is a mode of 3. This is 2 circles mode 2. This is 1 circle mode 1. So those results observed in the lab without any post processing. So this is still the raw data. You can see that we can't see those vortex beams in the in the free space by naked eyes, but those can be captured by the VNA by doing the planar scanning. And in the nature, those kind of vortex beam, you might already seen that. It's because in some extreme weather, you see the vortex shape like a cyclone or typhoon. Those are vortex shape, but this is similar thing, but it's just different. We are talking about different meaning because this is EM waves, but they are there. The fourth example we want to share is by still we shape the waveframes of the EM waves by using the metasurface. This time we play with circular polarized input, which means if we have a circular polarized input by using the same metasurface without changing the metasurface, we can convert this input into different mode, different vortex beam with different mode. For example, if the input is using the same metasurface, if the input is a right-hand circular polarization, and it can be converted to mode 1, mode 2, or whatever mode you wish. And if it's a left-hand polarization, circular polarization, it can be converted to mode 2, 3, or 4, or even higher. So it's a very flexible design. So I want to read out those ideas. It's a very interesting work. So this time, because this requires even harder phase calculation and require more than much more than 8 elements to achieve this performance. In this design, we applied 8x8 elements, unit cells for making this metasurface design. It takes quite some time to optimize those meta unit cells to achieve the required performance. Again, we use antenna phase delay line and antenna concept. We apply the principle of PB phase plus dynamic phase shift. Dynamic phase shift is using the transmission line concept. It's just a lot of effort to do the optimization. Ideally, AI technically can be applied for this design, but we didn't use AI. We still use our experience to make it. So thanks to the first author, Dr. Jianfeng Zhu, who made a lot of effort on this design. This is the measured and simulated vortex beam you can see from here with a required wavefront shaping. It's published on the Laser and Photonics Review. It's very interesting design. Again, we use the same set of meta unit cells, and we also try different functions, focusing function. You can see that the beam can be focused at a certain point in 3D. So other than the meta surfaces, we also applied the AME technique for making the microwave circuits. A few years, 3 years ago, we tried to achieve the bandpass filter design by vertically design the resonators and the transmission lines. You can see that this is a two-port network, and the signals coming from port 1 all the way through the resonators, and we measure the filtering performance at port 2. We applied the multiple layers. Here shows that this is a 5-layer design, and the spacing between the layers also given here. So this is side view, and this is a 3D view. Different color here shows different the patches on different layers. So this is this is like step into impedance matching, and also with the microstrip line resonators. This is fabricated 3D printed filter. You can see if you put it on your finger, it's really, really tiny. It's only about 2.7 by 1.4 by 0.5 cubic millimeter. In terms of wavelengths, it's even smaller. But because this is the very first design we made many years ago, so we couldn't manage the interconnection problem, which may cause the interconnection loss, and and also some the calibration wasn't done properly. That's why you can see the discrepancy between the measured insertion loss and the simulated insertion loss. The measured one is 3.242, and the simulated is less than 2, is 1 point something. Again, the insertion loss could be improved by improving the materials loss tangent parameter, and our industry partners at the moment is working on better materials with lower loss tangent. I think the microwave designers are really keen on that. This is another design we achieved. It's about a bandpass filter design again, but this time we use different concept. We use the vertically, we call that vertically integrated composite right-hand, left-handed transmission lines. And we apply those transmission, we propose those kind of vertical transmission line concept first, and then apply it to the bandpass filter design and the coupler design. So those kind of concepts being verified in planar structures being published many years ago. But we verify this concept by using 3D printing and vertically stacking those structures to miniaturize this design. So if you can see here, this is a typical SMK connector. The filter itself is only that small. But if you look at the performance, even the material is lossy. If you look at the performance between the measurement and simulation, this time we managed to calibrate it properly, and so we achieved a very good measured result comparing with the simulated one. You can see that the loss tangent, the insertion loss is only 1.7 dB, and the center frequency is 6.65 gigahertz, and the bandwidth is pretty good. Because of the multiple poles generated, it can achieve more than 71%, and again, it's very, very compact. This is still applying the vertically integrated CRL hand transmission lines, and we achieved a wideband coupler designs. So if you look at this design, so the bandwidth is really, really wide. So if you look at the phase imbalance and amplitude imbalance, so the bandwidth can be even around 70, more than 70%. If you are requiring a phase imbalance less than plus minus 3 degrees. So this is very good for the communication system that requiring the good phase balance, and the magnitude balance is even better. You can see that it can be the bandwidth is 55% for the plus minus 1 dB. Again, it's very, very tiny. So other designs I'd like to show here is like a phase zone plate. The idea was coming from the lighthouse that for Australia, there are many of those kind of lighthouses along the coast. They were designed for the optical applications with a super large aperture, but because we want to verify the concept by using 3D printing, and so we achieved this kind of concept at 75 gigahertz or 120 gigahertz. So this is not planar design, non-planar design. If you see that there are some raised dielectric rings on top of the top surface, this just help to reduce the side lobe by around 6 dB by using these raised dielectric rings. So this was done 3 years ago. So if you're interested, have a look at this paper. That's the design, our first design in the sub-terahertz range. Recently, we also verified the concept about the transmissive and reflexive metasurface design, which could be potentially used for beyond 5G or 6G communications that we introduced in the background section. This metasurface can actually reflect some of signal to one side and transmit some of signal to the other side, which, as shown here, we demonstrated that this can generate four beams, two on one side, two on the other side, with different orthogonal modes. This is very important for the wireless communication system because those modes are quadruple, can be used for quadruplexing channels, which means they are two orthogonal to each other. This is very interesting because we achieve this kind of performance at the physical layers. So the signal processing engineers, they can reduce some workload for them for the multi-channel communication system. Yeah, other than the communication, wireless communication or RF applications, we also work on the 3D printed ECG sensors. This is just one video recorded by my final year project student. We call that capstone project. Mr. Louis Millington, and he 3D printed this ECG sensor and applied on his body, and he detected his heart wave. Let's have a look at this video. This is a real-time heart wave detected by using this 3D printed ECG sensor. This is a sensor without packaging, and you can see that we can observe his heart wave on the oscilloscope. So applications. So we had a quick look about what can be done by using the emerging advanced additive manufacturing technology. Then let's have a look of some of the potential applications, right? So the first one will be this this demonstration. We work together with our collaborators from MIT and Scott and another group from Tsinghua University. So because of the space issue that we haven't been able to put the Professor Lee's group here. So actually this design was designed for the center frequency 140 gigahertz with a pencil beam generation. Without our 3D printed lens, the 140 gigahertz radar front end can generate a very wide beam, as shown here, with lower gain. But applying our meta lens, we can shape the beam with very narrow wavefront. So we successfully improved the gain by 16 dB, which means that the ERP being improved by 16 dB, boost the signal up to 25.2 dBn. This is really a lot for the RF front end. So if you look at here, because this lens was particularly co-designed with on-chip antennas, which was done by the first author, Mr. CB Chen, and so we co-designed this on-chip antenna and the lens part together. So this is an assembled picture, and this is the measured performance. So probably I can show this video recorded by the first author, Chen Xibi, about this radar sensor at 140 gigahertz. Let's have a look at this video. I can't hear it properly, so I just muted. So I hope you can see the video properly. So it shows that this radar is used to detect the targets at around 74 centimeter, but it can be used for longer range. This is only showing a real-time demonstration that, so we want to see a clear peak signal. That's why we put it in the 74 centimeter range. This is shows that the speed detection. You can see that on this screen, it shows how fast the target is moving. It gives you the speed of this target. Again, this is measured in the lab, and also by applying those kind of 140 gigahertz radar front end together with our 3D printed lens. So if you are interested, feel free to look at this video again, and it's also, the paper also published on ISSCC and also GSSC. There's some other potential applications, for example, the satellite applications. So this video was made by the publisher Wiley, and we can have a look of this some potential application for satellite communications. So Professor Baki, can you hear properly, or from my side I can't hear the video clearly?
Yes, I can hear you. I can also see the video.
Okay.
So, Dr. Yang, was it 64 different types of meta items?
Sorry, I missed your.
Oh, just what I have seen, it was written there that is 64 meta atoms. My question is it 16 different types or identical types?
64, 8 by 8. 64 different unit cells.
Different characteristics. Am I right? Or same
Uh,
characteristic?
64 different performance for
Different
the
performance. Okay, I got it.
yeah. I can't hear you clearly if somehow. I don't know if it's the internet problem or can you hear me clearly?
Yes, I can.
Okay. Yeah, because I don't know. Maybe I just stop playing this video. Otherwise, maybe the bandwidth is being affected. I don't know because I can't hear you clearly. Yeah. Do you want me to continue play or I just skip this part?
You can. I think you can skip.
Okay. Yeah. Okay. I'll skip this part because the video is available on the website, and if anyone interested, we can share the video.
Okay.
Okay. All right. Yeah, I think we are running out of time. So conclusions. Today, I'm very glad to share some of the recent progress regarding the additive manufacturing electronics, particularly for the circuits, antenna, and meter surface designs. And we are talking about the why we use 3D printing and what can be done, and also from microwave to the sub-terahertz range, that what can be achieved. So the next stage, we further engage with the companies and the industry people from different sectors, from space, semiconductor, and all those 3D printed electronics, and for wireless communications and sensing. Acknowledgement goes to the my team members and working in this particular range, and also our industry partners, particularly from Nano Dimension. I've been working. Thank you so much for their support from their engineer and technical side, and also the UTS Portal Space technical support team. So many of the designs were supported by Nano Dimension, and they are looking at some potentials for future communications and the 3D printed electronics. Also, the acknowledgement goes to my colleagues here, Associate Professor Pei Yanqing, who initiated the antenna chamber setup and benefited a lot of colleagues here at UTS. So we measure those meter surface at the antenna chamber for different polarizations in the Ka band. So this is my lab in the UTS Tech Lab, wireless lab. A lot of millimeter wave and terahertz setups, all the way up to 700 gigahertz. So yeah, a lot of facilities for the millimeter wave and terahertz test. And also we thank the collaborators in Australia who contributed the terahertz beam measurement platform, and the Center of Excellence for Transformative Meta-Optical Systems. So thank you so much. And if you have any questions, please let me know, or we can exchange ideas through emails if you wish.
Thank you, Dr. Yang. And now, Savia, you can check if there is any question from the audience side.
Okay, sir. Thank you so much to our honorable speaker for the wonderful presentation. The session was so knowledgeable. I think we gain valuable insight into the session. We look forward to apply the newfound knowledge to enhance our understanding and further contribute to our shared goal. Now we are almost at the end of our sessions. Now I would like to conduct a quick question answer session. Feel free to ask your question by opening your mic or write them at the chat box.
Sorry, sir. I can't hear you clearly. It's, maybe I turn off the camera and see if it's a bandwidth issue. I didn't get your question. Sabiha, did you ask question or?
Yes, sir. Sir,
No,
can you hear me?
actually, Dr. Young, actually, Savia is asking questions from the audience. If there is any questions from the audience side, then they are free to ask you question directly. They can ask question directly to you, or they can post their question in the chat box. So we wait, sir, for some moment to see whether if there is any question from the audience side. If there is, I guess no questions so far. So Savia, you can move on to the next part.
Okay, sir. Now we want to give a token of gratitude to our honorable keynote speaker for his brilliant and interactive sessions. Due to online, we will show the token of gratitude in screen share.
Dr. Young, please stop sharing your screen.
Yep. Yeah, let's see.
So this is for you, since this is online, Dr. Young. This is for you from our students of IEEE branch.
Oh, thank you so much, Professor Baki. Thank you.
Now I would like to now we want to give a token of gratitude to our honorable VC sir, former VC sir, our chief guest, Fazil Lahi sir, for his presence in the sessions.
I am not sure. VC sir has dropped a message to me. He has another meeting, and he also thanked Dr. Young. So, on behalf of Professor Dr. Fazle Ilahi sir, I'm accepting the request. Thanks, Savia.
Thank you.
May I conclude the session, sir?
So, yeah, Dr. Young, again, thank you for your valuable presentation. It was very comprehensive presentation, yeah, and enlightening. I think we're at the end of this session, and I will be in touch with you, Dr. Young. And I think, do you like to add anything from your side before we conclude?
I think I just missed the last few questions because conversations because I couldn't hear properly, so I stopped the video and restarted again. So looks better now. I can hear clearly. So I just want to make sure I didn't miss anything important.
No, sir.
Yeah, you didn't miss anything from our side.
Okay, thank you so much. So again, if anyone, any colleagues or friends they are interested in this 3D printing technology, feel free to reach out. Or we're happy to share or find collaboration opportunities.
So,
thank you.
Sabia, you can. I think we can conclude. Sabia, from your side, you also
Yes,
can
sir.
conclude.
Now we are going to conclude the sessions. Once again, thank you so much all for being part of the webinar. We hope this session has provided valuable insight and look forward to more engaging session in the future. Thank you so much, sir. Yang again for the wonderful sessions and there's the session was so excellent and thank you so much